Hi, everyone. Thank you so much for your patience. I know we're running late. So this talk is going to be very technical. I hope you're informed. Yeah, the, usually we overlook a lot of problems that come that don't really seem like problems until it's 3 a.m. and you realize the cluster is down and you have to fix it. And the entire cluster is unresponsive. One of such problems is etcd. Um, I'm sure you all know what etcd is. It's just that it's one of those things that you don't care until you should care. So I'm going to walk you through 6 common cases where etcd can fail and what you can do to rectify those, diagnose the problem, what you can do about it. And in production, these are well tested failure scenarios, and you will have a deeper look at each failure and how to address those and how to come up with a plan of action. A little bit about me. I'm right now pe- managing people, but I used to be a solutions engineer previously at all those companies. I live in the Silicon Valley. I came from California. I'm originally Indian, but I live in the US. I'm now American. Um, but I enjoy speaking. I like hiking. I spoke at a couple of other KCDs. Lima was one of those, Texas, DC. I also speak at KubeCon. I did not include that there, but I'm a regular speaker at some of these Kubernetes events. So here's the roadmap for today's session, right? I will walk you through, how what 6 failure scenarios, and I'll also help you. This is not roughly in an order of commonly how I saw in the wild issues happen. The first thing is going to be HCD's role in control plane and how where failures can happen, like slow disks, noisy neighbors, network latency issues. And each section will cover the symptoms, the diagnosis, and how you go about setting up specific Prometheus metrics and alerts if you want to. There's also a tool called HCD Diagnosis. If you are aware, it's written by VMware. I'll go a little bit into that. Please interrupt me if you have any questions. I've been fairly not technical recently, but I can still jog my memory and help you if I can. So first thing, I'm preaching to the choir here. I'm sure you know what etcd is, but if there's any beginners in the room, etcd is an open source distributed key value store. I'm looking at the laptop because it's kind of hard for me to look there, so I'm using the screen as a just I don't want you to be distracted. So I'll keep looking down and occasionally look at you. So yeah, etcd is an open source distributed key value store. It's widely used across not just Kubernetes, it's used outside of Kubernetes also. It was originally written by CoreOS in 2013. It combined 2 different ideas. One is Unix config files, the directory where the configs are stored, and the whole concept of distributed computing. That's two. They combined both and they created this etcd value store, key value store. And it uses Raft consensus algorithm. How many of you know Raft? I'm sure some of you know. Yeah, so Raft is pretty popular in distributed world. It follows the same methodology here also. It has to maintain consistency across cluster. There are a cluster of nodes, and you have to make sure somehow the cap theorem is maintained. Raft helps with that consensus, and etcd follows the same Raft protocol. So there are writes that go through a single leader, and there are followers, a bunch of them that needs to replicate. The leader has to replicate to the followers, and every time a write is written, it is written to a write ahead log, and before it is being acknowledged, the API server will wait, which means there are disk speed matters. It matters so much that if there's one slow follower, it's going to kill the latency and affect the entire etcd. And if etcd is down, the cluster is down. Unfortunately, it's a cascading impact. And then it also follows MVCC, which is multi-version concurrency control protocol, meaning that it maintains a full version of history for every key. It's kind of overhead also, but it just follows that protocol. So before we actually walk into the failure, I'd like to be precise what etcd actually does, because a lot of failure boards make sense only if you know the architecture. So I'll keep it short. Kubernetes objects like your config map, secrets, RBACs, your custom resources, they all are stored in etcd, right? And then API server is essentially a layer on top of this etcd, that will help with authentication, your admission control, and validation on top of the HCD. And then the critical thing is to understand in this context is the write path, how the writes are written to HCD. When you run the kubectl apply, the API server will actually call the HCD in a synchronous fashion. So it will basically wait for the acknowledgements to come from the leader. So the HCD the API server will send the request, the HCD will write to the write-ahead log, as I said before, and then there's a quorum of followers. If you know, in the distributed world, there's a quorum that has to be maintained in order to make sure that their messages are acknowledged. And then the fsync is a function that has to be synced back to the disk. All of this has to happen, and then we need to also make sure that the latency is down and network is up. We need to take care of all of these things when you're maintaining HCD. And then there's controller and scheduler that are attached to HCD. They use the long-lived watch connection. They are basically polling continuously to make sure that all the HCD, if HCD is slow, the controller will go slow. When controller is slow, the deployments will stop, and then all the HPA scaling will stop, and you basically have the whole reactive loop that will break. And then Raft protocol again, as I said, one node is a leader, followers, and you have a quorum. And then there's a network latency, members, they all have to be always highly available. It's very critical for every single write path. Now, I want to walk you through each of the root causes. As I said, I'll walk one root cause by another one at a time, and I'll go deep dive into each of those. The first one, let me be direct, right? All the slow disks are the most common cause of HCD degradations I saw in production. So slow disks are basically, they don't show up as like super direct. Like these don't come across as disk problems. They'll actually slowly start showing as API server timeouts, controller failures, and like leader election problems. That's how they'll show up, and then eventually it will lead to HCD failing. So you have to be careful, because the fdatasync function, you see, it's a synchronous function. So this is a blocking synchronous function, meaning the API server will wait on this call. Imagine if your disk is taking 50 milliseconds to fsync, which is totally normal in a network attached volume like EBS. But that 50 milliseconds for an API server, it will add latency for every write, meaning which under load, and if you're writing multiple such writes, you get queue buildup, and it will cascadingly become slow. And the danger in this threshold is that if for example, if the threshold is telling me 10 milliseconds P99 fsync latency, and above that, you'll start seeing the raft. If the latency is above that, you'll see the raft heartbeat going down. And above 50 milliseconds, you'll see the leader election happen. And worst part is, if it's above 100 milliseconds, you'll see that the cluster will actually completely be unavailable. Now, the culprit is usually what I've seen in the cloud native world is the EBS volumes. When you've run out of burst credits, the NFS mounts will, by the way, you should never use NFS for HCD. That's a first rule of thumb. If you do use, you'll run out of burst credits, and you'll see that the cloud instances are sharing disks with other container layers, and then it'll quickly start to fill up the kubelet logs. And then the fix is kind of non-negotiable here. You need to have dedicated NVMe with high IOPS SSD, so that you can exclusively use that for SSD, and other, if it's a cloud environment, you have to pick IO1, IO2, whichever has the highest IOPS. It's kind of, you have to spend for what you need. And if it's bare metal, again, dedicated NVMe is non-negotiable. You have to make sure that it also sets IO nice to give it's kind of a setting. You don't have to memorize, but it's just a configuration that we noticed in production to give HCD dedicated resources. Second thing is noisy neighbor. So these problems are particularly insidious in Kubernetes, because Kubernetes is kind of encouraging all the workloads to be packaged at once. They highly recommend and kind of encourage that. But for components like HCD, especially in control plane, they are first-class citizens. So when it is a first-class citizen, you should not really just let it be another set of parts, right? You have to have a you'll repeatedly see these etcd nodes going down because they are clubbed with other logging event nodes or monitoring agent nodes and other CI/CD runners and even application workload nodes. So the what's going on here is when there's a logging agent, right, like Fluent D or other logging agent which is co-running with HCD, it will take up a lot of IO at the scheduler level, and then HCD's writes will be rescheduled. That there's kind of a competing situation where there's CPU contention happening between that logging agent and the HCD. So they can be competing for the same resource, and you want to avoid that. The only solution is isolation. You want to make sure that you taint the control plane and make sure that you could do the no schedule configuration that I'm showing on screen, and you that just so that the user workloads will not land there. They are separately maintained. And you also should use C groups to give HCD a guaranteed CPU allocation. Meaning, if you're running a large cluster, say 100 plus nodes, you have to consider putting HCD on a separate dedicated cluster cluster with instances, and also API server has to also have its own cluster if possible. If not, try to at least dedicate one set of cluster nodes for HCD. Usually in cloud environments of EKS, DKE, whatnot, they handle all these for you. You don't have to do. But if you are self-managing stuff, this is when things get tricky and you get cut corners and you want to pay less. Next one is, it's kind of my favorite, which is a Raft, like network latency and Raft and this whole confusion around. Raft is actually very beautiful, but it's also very sensitive when it comes to network conditions. What I've learned over the years is that every write that you write from an API server to the HCD is actually going through a rigorous process that I'm showing on the screen, where the leader will append the write ahead log and then sends the RPC call to all followers, and it waits for the quorum to acknowledge, as I said before, and then the commit happens. This is kind of time taking process, and it's happening for every single network hop. And then imagine if there are just 3 members, and then the 3 members, one of the member is taking 80 milliseconds, or whichever is the slowest member. That will be kind of the turnaround time for that particular hop. And that will decide the latency for that disk and that particular hop. Meaning, you have to, you really sometimes have no control on how slow these messages will go, because it's based on the size of the message and network availability and all of that. So what happens as a cascading effect is that because there's a slow member, the heartbeat interval will actually go down. The election time, what happens? If you know the inner workings of Kubernetes, what happens is when the election timeout goes above 1000 milliseconds, there will be a re-election happening. And you don't want re-elections. These re-elections keep happening because there's a timeout and nobody's doing anything, and there won't be any more progress. And it's kind of repeats in loop. This is it's kind of, if there's a noisy network also, and it'll add more fuel to the problem, more fuel to the fire, and the cluster is constantly re-electing, as I said. And then, so in this particular situation, what you could do is you could only choose to put the members in the same availability zone. That way you are avoiding large network hops, if possible. At the bare minimum, you should pick the same region. What you should avoid is cross-region, because it's not worth the latency cost that you're going to get. Possible use a regional cluster with cross-regional. If you really want cross-regional, then go for that app-level replication if you're going cross-regional. One thing people miss is the large Kubernetes objects. Sometimes all these config maps, all the other objects, like, they take up space. For example, if config map is taking 1000 kbs, as like 900 kbs on the screen, it gets replicated every member. There are like 7 members, for example. It gets replicated 7 times every write. So imagine this, right? And it keeps growing. And that's the reason why you want to keep these objects smaller as possible. And that's what HCD is designed for, smaller objects, not for large config maps or any other pod, product status, or any other metrics. Next one is I want to talk about a little bit about the sizing configurations. There's a misconception that if you have large number of members, you will have high fault tolerance, which is kind of partially true. You will get high tolerance, but you'll also, what that also means is that every write has to replicate those many number of times before it actually commits. That's a pain. That's kind of one of the pain points, and it will only increase the write latency linearly. What you want to like these are the production grade numbers that you want to. 3 is pretty much always okay for production, usually always approved. 5 is okay if the clusters are large, and if you want to make sure that when you need to span across multiple availability zones, you can go for 5. But 7 is almost never justified. You don't want the consensus when imagine the situation that there are 7 member nodes and there's one leader node, one thing goes down, there's kind of overhead that is created in terms of waiting for consensus from 6 other nodes to re-elect another node as if there's a network partition or something, it'll delay again. So you really don't want to go for 7 because that overhead will start hurting the write throughput noticeably. There's this other sizing issue that I want to highlight is the database size. You want to configure that to be 2 gigs. The maximum is 8 gigs. When you hit that quota, the 8 gig quota, the HCD will actually go into a read-only mode. You don't want that. When that happens, there will be no more writes that can happen, and eventually the cluster will be down. It's the worst part is that it will incrementally creep up. You will actually not know right away when this happens. So all these objects, the Kubernetes objects, all the events that are being persisted, with all these operators that are adding per pod objects will have to keep that in mind and make sure that the HCD is not filling up faster. One fix is a compaction that I'll talk in the next slide. Compaction is reducing the size of the files on the disk. One other operational point is that you can set the alert to be 3 gigs instead of 8 gigs so that you actually know when to react. Even before that you hit the wall, you'll know that you're approaching that threshold limit. Next thing is compaction. It's a lot of teams, they actually think, they don't realize that they're accumulating technical debt until they actually do. This is one of the reasons why, because HCD is going to store every version of every key by default. There's watch mechanism that the controllers are watching and they actually get notified. All these are events getting added to HCD. So which means that database is growing continuously. Unless you explicitly compact it, it is going to keep growing. And you have to stop that. Compaction will actually mark the old versions as reclaimable. There are some settings that you see on the screen. I recommend using mode as periodic and retention as 1 hour, which will tell the HCD to keep the 1 hour of revision history, and then it'll compact the older files. For most clusters, this will work because the controllers are going to resync after startup anyway. One thing people will be surprised is that compaction is not actually shrinking the database file itself. It'll just claim that spot as reusable, but it won't shrink the file. What you have to do is make sure that you run a defragmentation where you identify the DB sizes going over a particular size. So what you need to do is you have to make sure that you wait for the clusters to stabilize one member at a time. You take your time to run the defrag script. Maybe you have a cron or some other maintenance script that takes care of the compaction. And on the other side, parallelly, you run the defrag on a monthly basis during a low traffic time frame. And then that way you can do the health checks one at a time and make sure that the cluster is not down. Because one operational challenge is that this defragmentation will cause the HCD to go into a lock mode. This is a fact. So usually it'll take few seconds lock, sometimes it's minutes also based on the size of the DB. In order to avoid that, maybe you should employ something like taking one member at a time and running these defragmentation scripts. That way you can clear up the database sizes. Now the another one is you also want to make sure you take snapshots. When you run the HCD CTL snapshot save, this is simple and fast. You can just take point-in time snapshots for the entire database. So you should be running this every 30 to 60 minutes and then move those snapshots to another object storage like S3 and GCS. And because you should at least have 30-minute RPO, because you can You don't want to, you sometimes cannot even afford losing 30 minutes worth of cluster state, right, when failure happens. So it's very critical. And then the verification step is also crucial. Most people don't do this, where HCD, CTL snapshot status, because some snapshots are corrupted and you don't know that it's corrupted until you want to restore it. When at 2 a.m. you realize that I want to check it and back up and restore this backup and realize the snapshot is corrupted. So what you want to do is in parallel run the snapshot status on file so you also know that this validation passed. Coming to encryption, Kubernetes secrets are all stored in etcd in the form of plain text. If somebody gets access to that store, you have all your secrets exposed. So what you want to do is you want to enable encryption at rest, even before, through the API calls, even before the data enters the etcd on API server. So yeah, restore process. Yeah, there are commands for restoring also. You need to update your API server whenever you restore. You need to redirect. Of course, this is like really obvious. You have to route that to point the new cluster directory. One thing is you have to keep practicing this and also know that you have to know your RTOs beforehand. That way you can time these backups and restores appropriately. So some of the metrics I gathered here is some of the Prometheus metrics that I thought this can be an operational cheat sheet for you if you want to quickly address some of the threshold issues or health concerns. If like the first two are the disk metrics. If the write ahead lock fsync is slow, your disk is the problem. If the backend commit is slow, then and the wall fsync is fine, you might have to look at the DB size or compaction issues. Moving on to leader changes. Leader changes are basically rate metrics. There are few changes over the lifetime. If there is only few changes over the lifetime of a cluster, that is fine. But if you see like 3 changes every hour, that is kind of chronically alarming problem. So you have to look at either network or disk or CPU starvation, whatnot. That's an alarming alert. You have to be ready to take care of. Next is DB size metrics. They're critical for capacity planning. You have to watch out for the ratio between the DB size that is in use versus total. If the in use percentage is 40% of the total, meaning that there's significant fragmentation, you have to run defrag there. Yeah, for all these, I recommend setting up Grafana dashboards with a 7-day history, or whichever your company, the interval that they allow, and make sure that you have point in time values, not just point in time values, over a window of time frame you can gather. If a disk is at like P99 15 milliseconds today and it was at 5 milliseconds last week, that is also kind of that needs attention. Even though the 15 milliseconds is not visibly causing any failures, you can draw some patterns by looking at these metrics in your Grafana dashboards. One more thing I wanted to mention is HCD diagnosis tool. It's one of the open source tools that VMware wrote. Because normally that all the metrics I mentioned, all the health checks that you want to do, that needs deeper familiarity of HCD, right? You have to know what these metrics actually mean. But manually collecting these evidences can be time taking, and also not much talent pool is there to do that. So if you want to rely on a tool, HCD diagnosis is for you. At the core, this is kind of, it runs one command, which is HCD diagnosis report, which will generate comprehensive report that will give you all the information like disk IO, your HCD health. It'll also give you a round trip time between the members and the resource pressures between the signals and all kind of relevant HCD metrics you can get, and make sure that leverage it in your own uh, as you see fit. Next thing is you want to design for resilience, meaning, as I said previously, you have to dedicate NVMe SSDs that are of high IOPS to HCD, so that for very large clusters, you need to, you have to identify clusters that will need certain separate clusters. Some of them don't even need. So we don't want to club all the different logging like containers and like some high churn, like low importance ones, maybe put them separately and have a separate one. Sometimes when it's low traffic, you can just make sure they're all in the same namespace. But yeah, so HCD is like very, like as I said, it needs a continuous maintenance, and you have to make sure that you take the snapshots when you start, and you also have to do it on a regular health check every time. One more thing I wanted to add was versions. when you have too many members and then different versions happening in the same, and you're upgrading from one version of Kubernetes to other, usually what happens is this, like one member will be on one version and the other member will be on the other version, so they'll be writing to a different leader, and then the election will happen. There's some inconsistency there, so you don't want to have too many like that problem I mentioned, too many learners or members issues. Make sure that you upgrade all of them at the same time. That's it. I thought I will put together everything I've learned. But just one thing I wanted to add is HCD is not a, it's not a fire and forget component. It needs care, some kind of love, and of course some good amount of disk. So make sure that you honor the storage requirements, and also make sure that you have you monitor all the right signals, and your Kubernetes cluster will be rock solid. And thank you so much for this opportunity.